where we left off in the last video. We'd expressed our line integral around the boundary of our surface. So this is f dot dr, where our path is this boundary right over here, this path C. We had expressed it in terms of a line integral around this boundary, around path C1, which is the boundary of region R. And the reason why this is going to be valuable to us is now we can directly apply Green's theorem to this to turn this into a double integral over this region right over here, the region that it is actually bounding. So let's actually do that. We're just applying Green's theorem here. So Green's theorem. And actually, let me box this off right over here. This was just something that we wrote to remind ourselves in the last video. So let me just box it off right over here. But when you apply Green's theorem, you get that this is going to be the exact same thing as the double integral over the region that C1 bounds, that region R that's in our xy plane, of the partial of this with respect to x. So the partial with respect to x, let me write that a little bit, partial with respect to x of this business. So I'll do that in that same green color. Q plus r times the partial of z with respect to y minus the partial with respect to y of p plus r times the partial of z with respect to x. P plus r times the partial of z with respect to x. And then dA, a little differential of our region. dA. And so let's actually calculate this right here. Let's actually you take the partials of each of these expressions. And we'll see that if we expand them and then simplify, we'll get something very similar, or actually hopefully identical to this right over here. And that'll show that this line integral for the special case is the same thing as this surface integral, which will prove Stokes' theorem for this special case. So let's do it. So let's just apply the partial derivative operator. So first we want to take the partial derivative with respect to q. And we need to remind ourselves, and we did this way up here where we first thought about it. We saw that q, well, p, q, and r, they're each functions of x, y, and z. So we're assuming that's how they're represented. And if z was not a function of x, then if we were to take the partial of q with respect to x, we would just write it as the partial of q with respect to x. But we know that we've assumed that z is itself a function of x and y. So if we're taking the partial with respect to x over here, we have to think first, well, how can q directly change with respect to x? And then how can it change due to something else changing due to x? And so that other thing that could change due to x is z. Y is independent of x, but z is a function of x. So let's keep that in mind. So we're really going to do the multivariable chain rule. So when we try to take the derivative of this part, we're taking essentially of this whole function with respect to x. We have to think about how will q change directly with respect to x. And to that, we have to add how q could change due to changes in other variables due to changes in x. And the other only variable that q is a function of that could change due to a change in x is z. So q could also change to z because z has changed due to x. So operated here is the partial with respect to x plus the partial of q with respect to z times the partial of z with respect to x. If q was purely, if we rewrote q so that z was substituted with x's and y's, because it is a function of x and y's, then we would just have to write this first term right over here. But we're assuming this is expressed as a function of x, y, and z itself is a function of x. And so that's why we had to use the multivariable chain rule. Now let's move to the next part. And both of these might have some x's in them. So we have to use the product rule right over here. So first we can take the derivative. First we could take the derivative of r with respect to x, and then multiply that times z sub y. And then we have to take the derivative of z sub y with respect to x and multiply that times r. So it's going to be, this is going to be plus, so the partial of, or if we take the derivative of this with respect to x, same exact logic. R can change directly due to x, and it can change due to y, and we want to and it can change due to z, and multiply that times how z could change due to x. Once again, that you could view this as the multivariable chain rule in action here. But of course, we take the derivative of the first term times the second term. I'll do the second term in magenta, times the second term. so the partial of z with respect to y, plus the derivative of the second term, which is the partial of z with respect to y, and then taking the partial of that with respect to x, which we could just write as that, times the first term, times our r. So that's the partial with respect to x of all of this business right over here. And then we need to subtract the partial of this with respect to y. And we're going to use the exact same logic. So then we're going to subtract, and I'll put it in parentheses like that. So p could change directly due to y. I will circle p. Let me do it with a color that I haven't used yet. P could change directly due to y. So this is so we could say the partial of p with respect to y. But it could also change due to z changing because of y. So plus the partial with respect to z times the partial of z with respect to y, plus, and I'll do r maybe in that same color, plus the derivative of r, well, we already figured that, but actually now it's with respect to x, not with respect to y. You have to be careful. So it's going to be the partial of r with respect to y plus the partial of r with respect to z times the partial of z with respect to y times z sub x times z sub x times z sub x plus, now we take the derivative of the second term times the first term. The derivative of the partial of z with respect to x then with respect to y is going to be the partial of z with respect to x, and then we're going to take the partial of that with respect to y, and then we're going to multiply that times r. And then we're going to multiply that times r. And now let's see if we can expand this out, and hopefully things simplify. And just a reminder, I'm just working on the inside of this double integral. I'll rewrite the outside, the double integral and the dA once I get this all cleaned up a little bit. So let me rewrite it a little bit. So this is equal to the partial of q. I'll try to color code it the same way. And this is really just algebra at this point. The partial of q with respect to x plus the partial of q with respect to z times the partial of z with respect to x plus the partial of r with respect to x times the partial of z with respect to y, and then plus the partial of r with respect to z times the partial of z with respect to x times the partial of z with respect to y. And then we have this term right over here, which I'll just do in purple, plus the partial of z with respect to y, and then with respect to x times r. And now we're going to subtract all of this business right over here. So minus, I'll do it in the blue, minus the partial of p with respect to y minus the partial of p with respect to z times the partial of z with respect to y. And then we're going to subtract from that minus the partial of r with respect to y times, we want to distribute this, times the partial of z with respect to x minus the partial of r. This gets a little bit tedious, but hopefully it'll get us to where we need to go. The partial of r with respect to z times the partial of z with respect to y times the partial of z with respect to x. And then finally this term right over here minus this, because we have that negative out there, minus the partial of z with respect to y, then with respect to x, and then with respect to y, r. And let's see if we can simplify things. So the first thing, this and this look to be the same. We just can commute the order in which we actually multiply. But these are the exact same terms. So that is going to cancel out with that. And because we assumed that because we assumed way up here that we have continuous second derivatives of the function z is a function of x and y, that is equal to that, we can now say that these two right over here are going to be the negatives of each other, or that they are going to cancel out. And so this simplified things a good bit. And let's see if I can write it in a way, let me group terms in a way that might start to make sense. And actually, I'm going to try to see if I can make them similar to this. So I have all the terms that have a z sub x, and the z sub y, and then the rest of them. So z sub x I'll do in blue. So you have the terms that have a z sub x in it. So you have this term right over here, and this term right over here. And we can factor out the z sub x, and we get the partial of z with respect to x times the partial of q with respect to z minus the partial of r with respect to y. And then let's do and I want to get the colors the same way too. I did yellow next. Plus, I have all the terms with the partial of z with respect to y. So it's that term and that term right over here. So it becomes plus the partial of z with respect to y times the partial of r with respect to x minus the partial of p with respect to z. And then we have these last two terms. And I used the color green up there, so I'll use the color green again. So for these two terms, I'll just write plus the partial of q with respect to x minus the partial of p with respect to y. So our double integrals has kind of, I can't really say simplified, but we can rewrite it like this. And we don't want to forget, this was all because this was all a simplification of our double integral over the region dA. This is what we have been able to, using Green's theorem and the multivariable chain rule and whatever else, we've been able to say that that line integral around the boundary of our surface is the same thing as this. And now we can compare that to what our surface integral was. So let's see if I have space. So copy, and then let me see if I have space up here to paste it. Well, it doesn't look like I actually have much space to paste it, although I'll try anyway. So if I paste it, you see that they are identical. They are identical. Our line integral is identical to this. We get the exact same thing. So our line integral, f dot dr around this pat c simplified to this, and our surface integral simplified to this. So using the assumptions we had, they both simplified to the same thing. So now we know for this special case, our line integral is equal to our surface integral. And we are done.